So in this video, we're going to find all higher derivatives of the following function. Of course, before we do that, I want to explain what exactly is a higher derivative. I write higher power derivative simply because it is written a couple of different ways. And the first model, the first way is, let's say for a function of y equals some polynomial, we would say that that if you wrote it like this, we know that that's find the derivative of the function y with respect to x. But essentially what we're doing is, for the first one, we can write that as y to this apostrophe here. That means take the first derivative of the function. We could also write that as f prime of x, or we could say the derivative d with respect to x for that function. So the next way, so this is the first derivative. The second derivative, so we can, and we're going to do this in a moment and see how this works, but we can say that it is y to the second prime. So that means take the first derivative and then take the derivative of that. We can also write it as f, and then like that. So like a quotation mark apparently. And so that's take it down to the second derivative, or we would write this as d d to the first to the second over dx, and then again we do the same thing here. So that's take it to the, or take the second derivative with respect to x of that function f of x. And the third is exactly the same, in that we will simply keep adding these little marks. This is the third, or d to the third. And actually, let me rewrite that. I do apologize. So this is a little simpler. I get so used to those little marks. So we're actually going to have just d to the second, x to the second. So that's take the second derivative of d with respect to x to the second. So that's essentially what we're saying. And again, to the third. So we can write a numerical value expressing what derivative that we're supposed to solve down for. So this is to the third, and that's of the function f of x. Okay, so and we can continue doing that to the fourth, to the fifth, and so on and so forth. You're going to find that for a polynomial, as we're going to work through right now, that it's going to solve itself down to 0. And it is important to note that when it asks for all derivatives, if you're working with a polynomial, you know that you're going to work that solution, that derivative, all the way down to 0. Let's go ahead and do that. So for this one, I'll move this over, make this a little easier. All right, so for this one, we're going to, and I'm simply going to write it as the derivative d with respect to x for f of x. And I write f of x because that represents what this function is, this polynomial, rather than having to write it over and over and over inside those brackets. So we're going to say the derivative of d with respect to x of the function f of x is, and from here for a polynomial it should be fairly simple. It's going to be 4 times the power of x, which is 4. So we're going to have 16 x to the fourth minus 1, which is 3, minus, and then we'll have 3 times 3 is 9, times x to the 3 minus 1 is going to give us x to the second, minus 5 times 2, which is 10, times x to the second minus 1, which is just x. And then, of course, we have a coefficient, a constant. Okay, so we have a term that has just a constant and nothing else. That's 0, so that's gone. You can see we're already reducing the number of terms each time we do this. So the next one is going to be the second derivative, d, with respect to x to the second x. So we're going to say that of the function f of x. And then here we're going to take 16 times 3. So we end up with 48 times x. And then you can see the powers start reducing as well. So it's x to the third minus 1 leaves us with 2. And then 9 times 2 is 18 to the x. And x to the second minus 1 leaves us with just x. And then we're going to have minus 10 times that first power here is just going to be 10. So we have reduced this down even further. So we're going to go d to the third. So the third derivative of this function. So we now have 48. 48 times 2, which gives us 96. And then it's x to the second minus 1 is just x, minus 18. And x to the first minus 1, that would be x to the 0, and x to the 0 is just going to be 1. That's why we're left with this. And again, minus 10, that becomes 0. So at our third derivative, we now have 2 terms. So then we have the derivative, the fourth derivative. So d of x4, and we're going to have the derivative of the function f of x. And then we end up with simply 96 times 1, and x to the first minus 1 is going to give us 1, so we end up with 96. And you would think, and I did at first, that you were done. But remember that you can take one more derivative anytime that you have just a constant. That's one of our derivative rules. So we're going to take the fifth and final derivative of this, such that the derivative of any constant is going to be 0. And I've shown this a few times how that works. But essentially 96 or any constant can be considered a polynomial in its most basic form. So if we say that 96 is a polynomial, polynomials we typically see x raised to a power. Well, it's x raised to 0 already. And we know that anything raised to a 0 power is just 1. So that's the same as 96 times 1. So that's essentially what we're doing, is we're taking that last step. So if we say that it is 96 times x to the 0, right? Well, we take the lead coefficient multiplied by the power of x, so that would be 96 multiplied by 0, multiplied by, and x to the 0 minus 1. Well, x to the 0 minus 1 leaves us with x to the negative 1. So this is rewritten as 96 times 0 over, and that's over x. And that leaves us with 0 over x and 0. And luckily, we do not have to show that work. We just know that any derivative of a constant is 0. Now, what we've done for these derivatives is we've taken each one that we have found, each one of these polynomials that we found, the derivative polynomial, and we place them in as the next function. That's what we're doing. So we're not doing anything fancy. We're just solving for each derivative, and then we're taking the next derivative of that function and the next one. So that's what this means. So I hope that helps, and thanks for watching.